is a magnetohydrodynamic craft? It is an aerospace craft propelled by magnetohydrodynamic MHD effects. Methods of propulsion and control: a heavier-than aircraft propelled by interaction of magnetic fields upon electrically conductive fluids such as plasma generated in air or water which surround the craft. The plasma is generated by means of the high DC potentials between the spaced electrodes, superconductor rings, through which a powerful current is caused to flow to induce a magnetic field, ionizing the region surrounding the craft. This means the craft looks like a glowing ball of light as it zooms through the air. Since plasmas absorb electromagnetic waves, it will be invisible to radar, as no EM waves will bounce back to the source. This craft flies on electrical principles, unlike the planes and helicopters of today that are more commonly known. Why haven't we seen the commercialization of the magnetohydrodynamic craft? There are several factors that add to the difficulty in fabricating and maintaining an MHD craft for regular use. MHD propulsion systems require large amounts of electrical power, which can be challenging to generate and store on an air or spacecraft. Magnetic materials such as iron, cobalt, nickel, neodymium, samarium, dysprosium have a high magnetic permeability and will need release to generate the magnetic fields required for MHD propulsion. MHD systems are relatively complex and require precise control of the electrical and magnetic fields to function effectively. As the understanding of plasma physics is still relatively in its infancy, MHD systems are not as efficient as traditional propulsion systems, which can limit their practical application. The materials needed for such a craft are not inexpensive. Ceramics and refractory metals will be required for the main fuselage and supporting structures, as they must be able to withstand the high temperatures and pressures generated by the MHD propulsion system. Refractory metals will rapidly oxidize under high temperatures and will be sublimated, changed directly into vapor when heated, markedly with sufficient temperature. Some refractory metals, after oxidizing, can self-ignite in the air and even can burn with explosions. The problem of refractory metal oxidation under high temperatures has not been solved so far. While in contrast, materials such as carbon fiber composites that can withstand the structural loads of flight while being lightweight enough to minimize the weight of the MHD craft may seem desirable. Large-scale electrical forces utilized, however, if allowed to short into those same carbon fiber composites, also become an explosion and fire hazard. The same electromagnetic effects that ionize the air and provide an action force in a selected direction and reaction force in the opposite direction pursuant to Newton's third law of motion also cause a molecular bombardment that, to quote the inventor Nikola Tesla, I think to be the principal cause of the disintegration. You heard that correctly. Disintegration. The MHD crafts of the past that have been photographed or video recorded most likely are no longer functional due to the stresses this style of propulsion has on the materials utilized. The aforementioned superconductor rings will need a high critical temperature, Tc, and a high critical current density, Jc. High-temperature superconductor, or HTS, materials with a Tc above the boiling point of liquid nitrogen, 77 K, makes them more suitable than low-temperature superconductors, LTS, as they require less cooling. HTS materials such as YbCO, yttrium barium copper oxide, and BsCCO, bismuth strontium calcium copper oxide, are currently being researched for use in MHD systems. To more accurately understand the logistic difficulties involved, 77 Kelvin is just over 321 degrees below zero. In order to achieve and sustain the motive effects required by a heavier-than-air MHD craft, a plasma's minimum temperature, electron temperature relative to the ionization energy into the plasma density, must be at least 6,000 degrees Kelvin over 10,000 degrees Fahrenheit. So not only are we faced with the problem of molecular bombardment disintegrating the craft while in flight, effective cooling of the same superconductor rings directly exposed to the ionized plasma is another challenge. A possible solution lies in using iron instead of using the more expensive superconductive materials. As identified in the earliest of these UFO-style patents, iron allowed to heat to molten levels and contained in high-temperature tube-like ring structures, as iron's maximum permeability may be as much as 16 times greater than at ordinary temperatures, and superconducting properties have been observed in molten iron. Overall, while MHD propulsion systems offer the potential for high-speed, long-range flight, the difficulties in fabricating and maintaining MHD craft are significant and have yet to be fully overcome. Be sure to subscribe so that you don't miss any of the coming videos in this series, and also hit the like button to show your support of our work. We look forward to seeing you in the next video.